In this week and the next week, we're going to talk about the IO model. One interesting thing about this IO model is that lots of the problems that have been studied in this model are actually geometric problems. So it actually ties very nicely to the topic that we study here. Just a little bit of refresher, we talked about the IO model a little bit at the beginning of the course, but basically the story is that the traditional model of computation, which is a random access machine, which involves a memory and a CPU, is not sufficient for many applications. This is because in reality, it's because in reality we have a memory hierarchy. So therefore, the architecture of computers is actually much more complicated than that simple model. And this brings up many different issues such as CASP meshes, TLB meshes, branch mesh predictions, etc. that we have covered some of them in a bit detail earlier. The whole point behind the AI model is that it gives us a very simple model to capture the behavior of modern computers. The basic idea is that the sequential access is actually much faster in disk as well as in many different architectures compared to random access. Even though disks might appear that they are old technology, this phenomenon actually holds in many other situations where if you do a continuous access or sequential access of data, that is much faster than if you just do random access of data. For disk, there's a particular physical reasons, but in most other mediums, there are also other similar or different physical reasons for that. For example, SSDs also show a similar behavior that if you read consecutively, it's actually much faster than if you just read random bits from here and there. Again, I covered some of these issues earlier in the course. I'm not going to go over them again. There is this code that Lars has, and I think I really like it. It basically compares the difference in speed between accessing an element or a data that is stored in a register compared to data that is on the disk. So this problem of having slow disk actually shows up in many applications if you do not take specific actions to mitigate it. So one way to see this is look at this running time of your algorithm compared to the data size. In many algorithms, the following phenomena happens: that your running time is fast, then it gets a bit slower. Once your data gets larger, it gets slower, and then at some point, once you hit your memory size, once your data no longer fits in the memory, your running time essentially blows up. And this is a scalability problem. This is because your algorithm does not take into account that random access is not good. In other words, you do not have uniform access time to all the elements. To fix this issue, we'll look at the IO model. Again, this model, we have looked at it a little bit in the past, but basically just to set the terminology, we have the following problem. We have n elements that are on the disk, and that these nodes are instance size. We have b elements per block, so disk is divided into blocks of size b. Your memory size is m, it fits m items, and if your problem produces an output, the number of items in the output is denoted by t. And to measure the performance, we use IOs. We count the number of blocks that you read and you write in your algorithm instead of a typical runtime analysis. Some of the common bounds that in the IO model are scanning, sorting, permuting, and searching. So in the internal memory model, these things are very easy. Scanning n elements takes n time, permuting elements takes n time, sorting takes n log n, and searching, if you use a binary search tree, for example, or binary search, it takes log base 2 of n. In the IO model, these bounds are a bit more complicated. You don't need to memorize or look at them into more details for now, because we're going to look at them in more detail later on. But what we can note crucially here is that the searching gets a little bit faster because you get a base b of b here. Permuting gets more complicated compared to sorting, so permuting could actually be as slow as sorting, and scanning is very fast. And one thing that we have to emphasize here is that factor B is actually very important when it comes to these bounds, because B could actually be very big compared, for example, block size could be kilobytes or tens of kilobytes of data. So it could be, let's say, a factor of 10,000. So it's actually a very, very big factor. The log factor in comparison is not so big. And then I'm going to show you some examples for now, and then we're going to look at some more serious problems and applications later on. So just to give you an example, we can look at the problem of traversing a linked list. So imagine that I have a linked list that is stored on the disk, and the disk block size is 2. So the first 2 elements are in one block, the next 2 elements in the second block, etc. If you want to traverse this list in the internal memory, then it doesn't matter how you if you want to traverse the linked list, then it doesn't matter how this linked list is stored in the internal memory, because it just takes O(n) time. But if you store them on a disk, it actually matters, and now we can see why. So for example, if I want to traverse 1, 2, 3 all the way to 10, first I need to read this block. So I read block that contains elements 1 and 5. I don't need the 5, but the element 1 takes me to element 2. So I need to read the second block, contains 2 and 6. 6 is useless, so I just need 2. Then I read 3 and 8. Then I need 4 and 9, etc. If I continue this process, you'll see that after I read this block, then I need to read this block again, because after 4 comes 5. I have read this block once before, but since my memory is not big enough to contain this block, I have actually forgotten about this block. This block has been erased from my memory because my memory can only store 2 blocks. Okay, and I read this at the beginning, I don't remember it anymore. So if you just continue doing this, you will see that I will need to read every single block twice to traverse this linked list. That is obviously very inefficient. Whereas if you had stored the elements in this order, you'll see that you will need to traverse every block. We need to read every block exactly once. So you first read one block, the first block. It contains elements 1 and 2. So you go from 1 to 2. That comes for free because both elements are inside memory. Then you read the next block. Again, that takes you to elements 3 and 4. Then you read 5 and 6, 7, 8, and 9, 10. So if you store the elements in this way on the disk, it is actually much faster to traverse, and we need half the block time, block reads. And in an algorithm like this, the I/O time is actually going to be dominating factor. So even though internally you do not do any different, the same number of operations, in other words, your pseudocode is exactly the same, your algorithm is exactly the same, it's just the way you store elements that is different. But because disk is going to be very slow, the amount of time you need to wait for the disk dominates the runtime of the algorithm. So basically what I mean is that the algorithm 2 is going to be roughly twice faster than algorithm 1, even though the only thing that is different between them is how you store the elements. And that's actually the most important problem in the I model. Given a bunch of elements or some data, how do we store them on the disk? And which algorithms we use to store them, and which algorithm we use to read them. And that's essentially the fundamental problems in the I model.